Okay, good morning guys. Assalamualaikum warahmatullah. Salam sejahtera. Uh, I wanted to take this opportunity to look at 4-bar linkages and try to review some of the problems associated with 4-bar linkages that I think students might have problem in trying to understand why we made certain assumptions. So I'm going to try to simplify and see how we can use this new way of looking at the problem and understanding the problem. So here are two same 4-bar linkages. The way we used to explain the 4-bar linkages and try to find the equation was to use the relative motion analysis. Or so what we do was first to draw the XY system. So yeah, and then what we did was we draw the position vector. This is position AB, and finally this is the position vector B. Position vector B relative to O is equals to position vector A relative to O versus position B relative to A. So from there, we usually write down our position vector equation. So we would write down position vector B relative to O because O is not moving, so we can write it as absolute vector, position vector B equals to position vector A relative to O. O is not moving again. I can remove O. Okay. And I can write down position vector B relative to A. From there, we can get the velocity equation VB equals to VA plus VB relative to A. There's a procedure to it, but I'll just simplify it. And also the second step was to get the acceleration equation. AB equals to acceleration A plus the relative acceleration B to A. So the problem arises when we wanted to find VB, for example. So the problem arises when we want to find VB. Students would usually go and write, and they said that VB equals to omega. Some of the mistakes say they said omega OB cross position vector B relative to O. Okay, yeah, because they saw this link, they saw this as a link, and they think that there's OB, so therefore they look at link OB and position vector B relative to O. But the link does not exist, so I have to write it down. The link does not exist. The link doesn't exist. No link. The link doesn't exist. It's only a drawing, so I can rub that out. So I said the link doesn't exist, but it's very difficult. I keep on finding or facing the same problem over the years, because students said, okay, whenever they wrote this vector, they would say that is VB equals to omega OB, but cross position vector B relative to O. So I thought that in order to overcome these difficulties, I said maybe I need to have, why not we try a new approach. So let me again put this, a new approach. Not really new, but to me it's new in terms of teaching. So this is the position vector A relative to O. So we know O is not owing, so we can, and this is position vector B relative to A. And this is position vector B relative to C. This is position vector C relative to B. And we have got to go back to O. Yeah, it is position vector C relative to O. Or we could replace, not closing the loop, but we could decide that, okay, we don't do this. We say that, why don't we say this is position vector B relative to C. But there is no link there. The problem is there is no link BC. So what we need to do is we need to find the vector that give us the link. So why don't we do this? We said that vector B relative to C equals to vector OC, vector C relative to O, and this is vector B relative to C. Yeah, so now I can use this to rewrite my equation back as position vector B relative to O. So this is position B relative to O. Yeah, B relative to O is not there, so O is not moving, so we can remove O. Position vector B equals to position vector A plus position vector B relative to A. Yeah. However, position vector B does not exist in that form. Okay. So B relative to O just now, we have to rewrite again. So we say that, why don't we say that position vector B relative to O equals to position vector C relative to O plus position vector B relative to C. So you can see there is a physical link here. There is a physical link of position vector C relative to O is here. It's here. Sorry. Vector C is relative to O is here, and position vector B relative to C, there is a physical link. Okay. What I wanted, there is a link. Okay. So moving on, if you took that approach and we apply it to the next thing, so let us rewrite again. Yeah, so here we have, let's use the blue as we use blue. So here is position vector A relative to again, yeah, and this is position vector B relative to A, and then you got this position vector B relative to O. So initially, what we used to do, we used to do this. We used to write position vector B relative to O because O is not moving, so I can remove O. But anyway, we'll maintain O. B equals to position vector A relative to O plus position vector B relative to A. That we have no issue with that, yeah. But what we wanted to do is now, say we take A, why not we replace B relative to O with position vector C relative to O plus position vector B relative to C. So why not, guys, we gantikan position vector B relative to O to position vector C relative to O plus position vector B relative to C. We don't have any problem there. So we can put that on the right hand side, or on the left hand side of the equation. So now, so we said we rewrite this equation back. Yeah, we rewrite again. So we said position vector C relative to O plus position vector B relative to C equals to position vector A relative to O plus position vector B relative to A. You don't have any problem. So then we can differentiate this position vector. So we say with d over dt, position vector C relative to O plus position vector B relative to C equals to d over dt, left and right hand side, both has got to be differentiated. So position vector A relative to O plus position vector B relative to A. So we know that position vector C relative to O is fixed. It's the ground, fixed, tak bergerak. So d over dt, position vector C relative to O equals to 0. C is fixed, tak bergerak. So therefore tak payah ulang-ulang. So we know that this is. So then, what about B relative to C? So B relative to C is also tak bergerak. So we have got, so then we only left with this equation. So then d over dt, position vector B relative to C, because it's a, so we get halaju VB relative to C. And we know that C is a fixed axis rotation. So we say that arm BC is a fixed rotation, fixed axis rotation. So what happened when we have a fixed axis rotation? So if we have a fixed axis rotation, it becomes like this. So VB relative to C, and C is not moving, so we can remove C. So I just cancel C here because C is fixed. C is fixed. And then we've got omega BC because of, and position vector B relative to C. Yeah. So we got then VB equals to omega BC cross position vector B relative to C. And that's the whole issue that I want to bring in. Similarly, if you use the same approach for acceleration, you will also get the same thing. So we know this is also fixed, and we do that. So, and then of course this will bring us to AB. Yeah. So then we get AB because fixed axis rotation. Kita ada alpha BC cross position vector B relative to C minus omega square position vector B relative to C. So that's also the way that a way to look at the problem. So it will not be confusing. What I wanted to show that we try not to think in terms of I'm trying to solve the misunderstanding that sometimes students have. So we did remove this, and we said that position vector B relative to O is equivalent to position C relative to O plus position B relative to C. And when we differentiate C relative to O, it's a fixed thing, it becomes 0, so that we get d over dt position C relative to O plus B relative to C. We get this RAO, and we got this term. Because C relative to O is fixed, we differentiate, we got 0. B relative to C, we got VB relative to C. And what does it say from this small exercise? Well, it says that if we look at this box here, yeah, and the answer that we get here, it would say that we can write it down, set d over dt position vector B relative to O equals to d over dt position vector C relative to O plus position vector B relative to C. And that is equals to, so we say that this is VB relative to O equals to VC relative to O. Because C relative to O is, sorry, this is 0. Let me correct. This is 0. This one is 0. B relative to C is VB relative to C. Yeah. So that is how I prove to you that VB relative to O equals to VB relative to C. So proved. So that I'm not sure whether it should be able to explain to you why. Oh, why is it that he's not? Why is it that I'm not taking the link OB? No, the link OB doesn't exist. The only thing physically exists is the connection OC and link BC. So rather than writing R position vector B relative to RB slash O, I would write position vector B relative to O is equals to position vector C relative to O, this one, plus this one, position B relative to C. So when I differentiate position d over dt C relative to O plus B relative to C, I got it fixed because C is fixed. So when you differentiate something constant, you get 0. And then you differentiate the position vector B relative to C, which is rotating around the fixed axis C. So its velocity B relative to C, we can find that omega BC cross position vector BC. This is not a big problem. So, and if you look at, if we look at detail, Here we can say that d over dt position vector b relative to O is velocity b relative to O. And when we differentiate the component c relative to O plus c position vector b relative to c, we get d over t 0 because c relative to O doesn't move at all, it's fixed. And then we got velocity of b relative to c. And this proves that relative vb relative to O equals to vb relative to c. And we know how to find vb relative to c. I hope that somewhat explained to you how we can solve the 4-bar linkages. Yeah, doesn't have to be long. So thank you very much. We'll see you in the next lecture.